everyone. Today you're going to learn about square numbers and square roots. So let's get started. So first we're going to learn how to find the square of a whole number. And that's what it's called, finding the square of a whole number. You know what we mean by whole numbers, right? That means it's a whole number. It's not divided into parts, not fractions or decimals, it's whole. So here we have a square, right? A square. And one side of it is 3 centimeters long. If it's a square, we know that all the sides are equal. So all the sides are 3 centimeters long. But what we don't know is what the area is. But I know you know, because you're very smart, and you know that the total area of the square is going to be the length times the width. And since we know it's a square, we can label this, right? That is also 3 centimeters. So the entire area is how much, everyone? 9 centimeters square. See that little exponent that I included right there? We do that because if we were to actually see, I know this isn't perfect. This doesn't look like 3 centimeters by 3 centimeters, so bear with me. If we were to draw those in and pretend that they're accurate, we would end up seeing 9 squares in the area of the square. Okay? But we write it like this, 9 centimeters square. Do you remember what this is called? That little number there? I know you do. It starts with an E, right? Did you say it? I hope Ms. Mosher heard you say it. That's an exponent. We're going to talk more about exponents, but now we can see why we do that. It forms a square. What we did to get that is 3 times 3. That was the length times the width. We can write that like this, 3 squared with the exponent, which tells us that you're multiplying 3 by itself 2 times. So 3 times 3 can be written like that. So far, so good? Okay, we're going to continue. So here's another one we're going to do. I'm not going to draw on the squares on this one, but I want to remind you that this is called finding the square of a whole number. So what is the square of 8? So to find that, you're thinking, well, what's the area of this entire square? And to find the area, you're thinking length times width. If I tell you that this is a square, we know the sides are equal. So you're going to find it by doing 8 times 8, right? Which equals 64. But if we're saying it's the area, we're talking about the space inside, which forms a square. So we'd say it's 64, oops, I didn't use centimeters on this one, I used inches. Inches square. Okay, so far so good? That's what we mean when we're finding, when we're talking about finding the square of a number. So the square of 8 is 64. There's another term I want to use with you. I want you to know, oops, the word base. And so this word, or this number here, is actually the base. 8. 8 is the base. Especially when we write it, I should write it like this. So 8 squared, this is all equal, right? 8 squared with the exponent 2. The 8 is considered the base. And the 2 is considered the, say it everyone. Okay, you should have said this word, exponent. Exponent. It is going up the side of my board. Okay, we're going to continue because now I want to go the opposite way. Now I want to talk about what perfect squares are. So when I say the opposite, now I'm talking about we know the area of the square inside, but we don't know the length of the sides of the square. But if we know this is a square, and we know that all the sides have to be equal, and the total area is equal to 25, we know that this side times this side equals 25. So what would that be? Something times the same thing. In algebra, we would use a variable, and it have to be the same one, right? So let's say it's a times a equals 25. What would that be? I'm going to erase this. I hope you said 5, because you know your multiplication facts, right? There's only one number that when multiplied by itself can equal 25. And we can also write that like this, 5 squared. So 5 is the base, again. But another way to say this is that we're looking for the square root of 25. The square root of 25. Perhaps you've seen it written like this. That means square root. Anytime you see that symbol, we say the square root of 25 is 5. And all that means is that 5 times 5 equals 25. 5 is the base, and the square root of 25 is 5. So far, so good? What we're going to be doing now is we're going to be trying to find square roots of numbers. And I want us to do an investigation. I want you to find all the perfect squares from 1 to 100. Did I really describe what perfect squares are? Hold on. I don't think I really talked about that. I have it here on the slide. So a perfect square is a whole number that is, their square root is a whole number. So 25 is considered a perfect square because 5 times 5, that's a whole number, equals 25. So what's another example of a perfect square? 16 is a perfect square because 4 times 4 equals 16. Do you see? 4 is a whole number, and 4 times itself equals 16. 5 times itself, 5 is a whole number, equals 25. 5 times 5 equals 25, so that makes 25 a perfect square. If you were to take all of you may have done this last year when you took tiles and you built a square with these numbers, it would form a perfect square. So my question to you is, what are all the perfect squares from 1 to 100? And I actually want you to press pause on the video, and I want you to find them. Go ahead. What are all the perfect squares from 1 to 100? As you got started, did you start to write a list like this? I have the perfect squares written in black, and I have a rationale for it in blue. 1 is a perfect square, isn't it? Because 1 times 1 equals 1. 4 is a perfect square because 2 times 2 equals 4. 9 is a perfect square because 3 times 3 equals 9. Are you getting all of these? Is it complete? Because I'm asking for 1 to 100. If not, press pause and find the rest of them. Okay, by now you should have gotten all of them. Does your list look like my list? We have all the perfect squares written in black, and we have our rationale for it, our proof, because whole numbers times themselves equal that number. Okay, why are we doing this? Well, you know how much I love prime factorizations, right? I want to give you another reason to love it. So our next part of this math investigation is, why does Ms. Drum think so highly of using prime factorizations? I would like you, prime factorizations of numbers. I didn't finish it. There's me thinking of a happy prime factorization. What I'd like you to do next is to take your perfect squares, and I want you to find the prime factorizations for all of them. So press pause again. Make your paper really nice and organized, and just write the prime factorizations for each of these numbers. It won't take you very long. I'll give you a hint. What's the prime factorization of our first one, number 1? Is there one? No, there isn't. So you can skip that one. There's no prime factorization because 1 isn't a prime number. But you can find them all for the others. Okay, go for it. Did you press pause? Press pause. Okay, did you find them? we're going to do a demonstration so that you can use that list of prime factorizations for each of the numbers so you can see why I think so highly of using the prime factorizations. We've done a lot with prime factorizations in the past few weeks, right? We've looked for the greatest common factor by using prime factorizations. We've looked for the least common multiple by using prime factorizations. Now we're going to use prime factorizations to help us find the square roots of numbers. Yes, you could use just your multiplication facts. I know you know that. So we're going to use 100 as our example. And if I were to ask you, what's the square root of 100? You probably already know, right? Remember that symbol? It's 10, right? Because 10 times 10 equals 100. So one method, I'll put a 1 there, for one method is knowing your multiplication facts. The square root of 100, and remember how we write that, equals 10. And we know that because 10 times 10 equals 100. Well, the problem with only having that method is that you're not always going to know the multiplication facts for numbers. What about numbers that are greater than 100? Perfect squares, there are perfect squares that exist that are greater, and you may not know the facts. So if we find the prime factorization, I'll show you how we can find that. Oh, I'm going to need an eraser to help me with this. So that's one method. Here's the second method, okay, using the prime factorization. This was my plan. Let me see. Yep, that's right. Okay, we're almost towards the end. So what is the prime factorization for 100? I'm listening. Okay, I think you're saying 2 times 2 times 5 times 5. Did you say that? Yes, of course you did. I'm sure you did. Okay, so here's our prime factorization for 100. What's interesting about the prime factorization is I'm seeing 2 2s and 2 5s. In a sense, I'm seeing 2 pairs of common numbers. I'm going to combine them so that I can make common pairs of prime factors in the prime factorization. So when I look at 2 and 5, and that would be multiplied, let me move this out of the way, times 2 times 5. We know that these equal 10, just like knowing our multiplication facts told us. But what's interesting about using prime factorizations is that when you look at the prime factorization, you can look for pairs. I compare this one with this one. I compare this one with this one. When you look at the prime factorizations, you can find those pairs of numbers, combine them. I shouldn't say pairs of numbers. You can find common, so you can combine them to discover what is the square root. Check your list of prime factorizations that I had you draw up and look for those pairs of prime factors and look to see if you can discover what the square roots are of each of those numbers. I hope you hit pause. So pause.